Hello. Welcome back. So it is my pleasure to introduce Maaike Zwart, who is joining us from Denmark, from the University of Copenhagen. She's an expert in monads and distributive laws, and I remember seeing a talk of her a few years ago where she was showing us how to show two monads don't distribute. And today's talk is going to be extending this to delay monads, I believe. Yeah. So take it away. Thank you.
Thank you so much for this nice introduction, and thank you, Marie, for the invitation to be here. It's my pleasure. As Vikram said, I will again show that distributive laws are not possible. It's sort of my thing. And it's because people keep asking questions. Questions like, does the power set monad distribute over the delay monad? This is the question that Rasmus Meulberg asked me 3 years ago when I joined his group. And the answer is no. And today I want to not only share the answer to this question with you, but I want to share my journey on how I discovered this. And I want to share all the cool results that we discovered on this journey in the meantime. But before I can share all these cool results in the whole journey, I need to unpack a few things. Like, I think most of you know what a monad is, but why are we interested in these things? What is the power set monad? What is the delay monad? And there's also a bit about distribution monad, and that is because actually the same proof that I have for the power set monad also works for distribution monad. But before I can tell you about that, I need to say what all of these things are. And then, of course, what does it mean to distribute? And why do we want to do that? Now, once I've introduced all of these concepts to you, most of them will be familiar, but just so we're all on the same page, then we can go on the journey. And for the power set monad, we will first try the obvious distributive laws. They are parallel and sequential computation, and this will make sense later in the talk. But we'll see that those fail. And actually, I wasn't the one discovering that they failed. It was my predecessor, Rasmus' previous postdoc, Andrea. But what is new is that we can see why it failed. And this is where the really interesting bit is. Discovering why it failed and what we can learn from that. And as I say here, small, it's not just because of idempotence. And that's because one of the nastiest properties of power set is idempotence. It's usually the culprit that makes everything go wrong. Also this time, but not just idempotence this time. There's more there that makes it go wrong. And then, well, after we've tried the obvious things, I'm going to show you that also non-obvious things will not work. It's completely impossible. So that's just what I do when people ask me this type of question. And this proof, it will also work for distributions, like I said. But then I'll finish off with a tiny bit of a positive message. I'll also look at free combinations of monads, so not distributive laws, but free combinations, and they can be interesting on their own. So that's the plan for today, but let's first get a bit of the definition so that we all know what this talk's really about. So, monads. We've seen quite a fair bit of monads today. We've seen several uses of them. And there was actually a slide in the previous talk that had a nice purple blob here on the bottom that was all about computational effects. It was an overview of like computer science, and the purple blob was not what I was pointing attention to. I should have grabbed this picture, but computational effects are the monads that I'm looking at. And that's because in functional programming languages, such as Haskell or lambda calculus, if you don't have monads, then all you have is equations. But equations don't make a computer do things. But what we want to use computers for is to do stuff, like print things, give output, throw exceptions if things go wrong, do probabilistic things, read things, write things. And all of that is done by monads if you use functional languages. So that's why monads are interesting and useful in my side of the research, at least. So they are models of computation. And what I'll be focusing on in this talk is non-determinism and probability. But there's a whole lot of other things. Now, what are monads, what we've seen plenty of times today, is that they're functors with some extra structure. Functors with a unit and a multiplication, satisfying some axioms. And the monads that I'm interested in are finitary monads. And they have this really nice property that you can also describe them algebraically. So you can describe them with a set of operations and some equations between them. And in type theory, you can do this with a higher inductive type, where the operation symbols are constructors, but then also the equations are constructors. Now let's see some examples of this, which will make it much more clear. So here is the power set monad. On the categorical side, this bit, you have a functor, unit, and multiplication. The functor takes a set X and maps it to the set containing all finite subsets of X. Then the unit takes an element of X and maps it to just a little singleton set. And the multiplication takes a union of sets. Now, hopefully that was known to most of you. But the algebraic side is what I really want to focus on. And this is where you can see that power set is a model for non-determinism. So here we have a unit and a binary symbol satisfying the unit equation, associativity, commutativity, and idempotence. Very simple algebraic theory. But really, if you interpret this as non-determinism, for instance, idempotence, if I choose non-deterministically between x and x, well, that's the same as just executing x. Commutativity, if I choose non-deterministically between x and y, well, that's the same as choosing non-deterministically between y and x. So in that way, it really makes sense to see non-determinism as this algebraic structure. And that's what we're going to look at in this talk. Now, there is a cousin of non-determinism, which is probabilistic choice, which is really much the same, except that instead of choosing non-deterministically, you choose probabilistically. So there's a little sort of plus p here, which says that with probability p, I choose x or y. And that's the only difference between power set and the distribution monad. There's probabilistic choice in one, non-deterministic choice in the other. So now you've already seen two of the three monads that I want to introduce. And hopefully these have been familiar. But the last one is a bit of a probably more unknown to you guys, which is the delay monad. This is a monad that Rasmus and I work a lot with, and it is to model recursion or iteration. And there's two versions of this delay monad. There's a co-inductive one and a guarded recursive one. And the co-inductive one is what I'll introduce first. That one is the easiest one to talk about in talks, so that's the one we'll be focusing on. And the other one, the guarded recursive one, is easier to work with in proofs, so that's what is more in my papers. But this one just gives a better overview. Let's see. So I have this recursive equation here. Delay of x is either x or delay of x. That's a recursive equation to define this monad. And this monad is the co-inductive solution to that equation. And it's a way to model iteration in type theory. So I have the unit of the monad is all the things that are available right now, which is just the in left. So we read this as an element of the delay monad X is either available right now, or it needs a computation step, which is sort of the in-write. That's why we call this step. In-write is called step because it means sort of we need a computation step before X is available. And then the multiplication of the monad is just, well, it has a computation that yields a computation that yields a value, and you just sort of smash that into one computation like this. So here I have a computation that takes one computation step and then yields a computation that takes two computation steps before yielding X. And my multiplication of the monad just squashes that 3 computation steps until you get X. So that's how the delay monad works. At least that's all you need to know for this talk. Then there is the guarded recursive little brother of this delay monad. And you see it's much the same, except there's a little kappa on top. That's a clock. So all of this before is you can do in any type theory you want, or even in set theory, but this guarded recursive delay monad is a thing that is modeled in clocked cubical type theory. And this kappa there is a clock. And it is a guarded version because now you see this little triangle here. So if I want to unfold the recursion, it's guarded by this triangle, and it means I need some evidence of a clock ticking before I can access it. And in this way, you can model recursion safely in type theory. Now, there's plenty of papers of Rasmus if you want to know more details about this. But it just means that if I want to now write the multiplication, so here, if I have some computation that takes a step, I can't access the result of that computation until an actual time step has happened, which is this sort of alpha as a tick on the clock. Once this has happened, I can access the next thing in my computation. So it's really modeling closely what a computer does. If a computer is computing, you don't know what the result is going to be. You have to wait. And that's what this guarded recursive version of the delay monad does. Now, these two are related. That's why they're both called delay monad, by quantifying over clock. So here you have this, by the way, just the recursive solution. And here you have the co-inductive solution. And if you quantify over all clocks, then you go from one to the other. But in this talk, I'm mostly going to focus on the co-inductive version because it's just way easier to talk about because we can see all of the steps, and it's easier. So that brings me to combining monads. Like, okay, we have monads that do computation steps, and I have monads for non-determinism and for probability. But what now if a program that I want to make in my type theory both uses recursion and non-deterministic choice? Well, then I need both of my monads in the same type theory. And that is achieved by combining the two monads. Now, what you can do is just a free combination. I just put all of the axioms of both monads just together, make a new monad of that, and then I have both effects into one. But then I don't have any interaction between the two effects. But it could be nice, and at the end of the talk I'll say a bit more about this. But my personal favorite way of combining monads is via a distributive law. And this distributive law allows you to have interaction between the two effects. And it's a bit like times and plus in numbers. They're not independent of each other. They can distribute, and I can calculate. If I have a big sum with pluses and times, I can distribute them over so I can actually calculate that sum. So now, if I have a distributive law, I can make a combined monad where time steps from the delay monad and non-deterministic choice are not just independent, but they interact. And I can figure out, I can actually compute things with them. So that is the goal. And that is what Rasmus asked of me. When he asked me, does the power set distribute over the delay monad? He asked me, is there a way to model interaction between the two in a way that forms a monad? Now, to find such a thing, a distributive law is a natural transformation of the type shown above, and it needs to satisfy some axioms. And this is just to make sure that the interaction between the delay steps and the non-deterministic choice, that they interact well with the monad structure of each separate monad. You don't need to remember these diagrams. I'll use one of them later on, but we'll get to that. It's just for a distributive law to work, it needs to satisfy this. That's all you need to know. So let's get to the actual question. Is there such a distributive law? Now, to find one, if we look at the type here, what we need to find is we're given something of PL. That is, we're given a set, and each of the elements of that set are computations that may need some computation steps to finish. So that is something like this. We have a set, and each of the elements, they need to compute. And then we can ask for such an element to compute, and then eventually it might yield a result. And I want to turn this into a computation that at the end of it returns a set, where I just have all of the elements. That is the quest. That's what I want to get to. Now, if we just look at that, there's two obvious ways of doing this, namely sequential and parallel computation. Sequential computation works like this. So, okay, I'm computing my set, and the way I'm doing that is by, under the hood, computing each element separately. And then once all the elements have computed, I give my end results like, ta-da, I have a set. That's sequential computation. And the total time it takes is the sum of all the computation times of each of the elements. Then we have parallel computation, which things like, oh, well, I can be a bit smarter about that. While I'm computing, I have several computer cores or something. I can just do all of this in parallel. I'm just starting computing all of my elements, and then some of them will finish, some take a bit longer. Then when all my elements have computed, ta-da, my answer. And this will take the maximum of the computation times of each element. So those are two obvious ways to define a map of this type. And the question is any of these two an actual distributive law? Well, you already know the question is no, but we're going to find out why. So let's first have a look at sequential computation. Here I've spelled out a bit more in detail how a distributive law would be defined using sequential computation. It's just if all the elements in my set are already available, then my entire set is available. If one of the elements still needs a computation step, then my entire set needs a computation step. So here's an illustration of how that works. If I have the set containing x, y, and z, but x is available after 2 computation steps, y is immediately available, and z takes 1 computation step, then by the principle of I take the sum of all the computation steps, this will be turned into the set x, y, and z available after 3 computation steps. That's how this candidate distributive law works. But is it a distributive law? Well, we know it's not. I've already told you. But why? Well, it is idempotence, that pesky little property of power set. And here is how that destroys our hope. So these two sets are the same. I have an element x available after 1 computation step. But because of idempotence, I can just have that element x available after 1 computation step twice in my set. It doesn't matter, same set. That's the idempotence property. But if I now apply my candidate distributive law, the first one is the singleton set X available after one computation step. Whereas the second one, well, it adds all the computation steps of my elements, so that is 2 computation steps. So now by just using idempotence, I can change how long it takes to compute my set. That's no good for a distributive law. So that doesn't work. Sequential computation's out of the window. And it's not only idempotence that can make me do this. So now I'm taking a step back, like not just looking at power set, but what if I changed my axioms a bit? What if I just looked at a different monad? Well, I could just have the axiom, I can't change a single x in 2 x's, but when I have 2 x's, then I can change them into 3. That's also, I can do the same trick. And or sometimes in algebraic theories, you see an axiom like this: x times x plus y is equal to x plus y. All of these equations are imbalanced. Like there's a different number of x's on the left-hand side than there is on the right-hand side. And as soon as you have such an imbalanced equation, then this argument holds. And it turns out that that is the only thing that goes wrong for a sequential computation. So that leads me to a result in our paper that is sequential computation is actually a distributive law if you're trying to distribute the delay monad, well, if you're trying to distribute a monad over the delay monad, and that monad is presented by an algebraic theory, and the algebraic theory only has balanced equations, then it works. So we found a distributive law, just not for the monad we wanted. Moving on. Let's try the other obvious candidate, parallel computation. Now, I've spelled out again in a bit more detail what parallel computation does. So it's still, if all the elements in my set are available, then the entire set is available. If one element still needs computation time, the whole set needs computation time. And now the difference is in this third line here. If I have multiple elements that need computation time, I can advance them parallel. So I only take one step out, and that changes the sum of computation times into the max. So I have this same set again, x, y, and z, x available after 2 steps, y available immediately, z available after 1. And now by parallel computation, this turns into the set x, y, and z available after just 2, the maximum number of computation steps. So that's parallel computation, a bit more detailed. And this is also not a distributive law. But this time, it's not because of idempotence. It is another thing that fails. And I want to show you what fails and what we can learn from that. And this time, we need one of those axioms from a distributive law. Remember, I had them up there earlier and told you not to worry. This one we actually need. So for parallel computation to be a distributive law, it needs to satisfy this diagram. So I want to go around this diagram with this element here. Now you see that there's 2 layers of computation here. So we're looking at a set containing computations that give back computations that give back elements. So that's the set I have here. It contains the computation that takes 1 step, then gives back the computation that has already finished and gives back x. My second element is a computation that has finished, and it gives back a computation that takes 1 step and then gives y. And this set I'm going to chase around the diagram. First, let's go down. And there we applied a multiplication of the delay monad. And that was just squishing all the computation steps. So what I get then is just x and y, each available after one computation step. So it's just, it squishes this step now to just step now. And same for the other one. Now, by parallel computation, I know that that one then becomes the set x and y available after the maximum number of computation steps, which is 1 in this case, because both x and y are available after one step. So that is if I go down and to the right. Now let's take the top root. And in the top root, same element, but now I apply my parallel computation to just the outer layer of computations. And my outer layer of computations, here I have 1 step, here I have 0 steps. So the maximum number of that is 1 step. And then I apply my parallel computation to the inner layer of computations. And here, the inner layer, I have 0 steps, and I have 1 step. And the maximum of that is 1 step here. Okay, so far so good. And then I apply my multiplication again, which is adding all the steps that I encounter. So that is 1, 2 steps. So 2 steps. Whoa, but hold on. 2 steps, 1 step. I again have this problem that if I take a different route through the diagram, one way I get 1 step, the other way I get 2 steps. That's not equal. So this means that parallel computation is also not a distributive law, which is okay. But I haven't used idempotence in this. So I told you, idempotence was not the only thing that went wrong. In fact, if we look at this proof, I haven't used any property of power set at all. Like, yeah, I write squarely brackets and a comma, but I don't use any properties of sets. I don't use units, associativity, commutativity, idempotence, none of them. So actually, this very same proof works with trees, multisets, lists, any sort of structure where I can put 2 elements in. Because that I need to do. I need to have 2 elements, otherwise this trick doesn't work. So what I've shown is that parallel computation is never a distributive law as long as I have some structure where I can put 2 different elements in. That's a bit of a negative result, but a really cool one. So yeah. Then going back to power set, we've seen that sequential computation doesn't work, and we've seen that parallel computation doesn't work. But maybe something more exotic can work, something I haven't thought of yet. Now it's time to think the other way, not just try things, but think, well, okay, suppose I have one, suppose I have a distributive law, what does it need to satisfy? So I've written out the 3 cases I had for parallel computation again, and I've grayed out some things. Because the first step, if all my elements are available right now in the set, my entire set needs to be available. That is a given. I can't change that. That is by the rules of a distributive law. But the other 2 cases, maybe we can come up with something clever to make it work. Well, let's take a look at the last one. So if I have a set with 2 elements, each needing a computation step, what can we do with that? Well, a distributive law is a natural transformation. So I've put here a naturality diagram where you see here's my distributive law that I don't know what it does yet. And here I look at a 2-element set, and I call the 2 elements x and y. And here I look at a 1-element set, just x. And I'm going to look at this element here and change it around that naturality diagram. And that will teach me what my distributive law could possibly do. So here I have a set with x and y, each available after one computation step. That's what I want. I want both my elements to have a computation step. Now, if I map this down according to this neutrality diagram, then I end up at a set with just the element x available after one step. And because of some of the axioms of distributive laws, I have to map this to the singleton set x available after one computation step. That's one of those triangle axioms of distributive law. There's no choice here. Every distributive law has to do this. And that means that I can learn something from taking the upper route. Because previously, every time I said that it wasn't a distributive law because there was a different number of steps. So now we can fix the number of steps. I don't know what my distributive law does yet, but this diagram needs to commute, so it better has the same number of steps, whatever I do. And then I can use that I have this just a set with two elements here, because now I have some set, which is a subset of a set of two elements, that is available after one step. Well, there's only 4 choices of a subset of a set of two elements. So I can just go by them one by one. I'm not going to do that in this talk. That's in my paper with Rasmus. But it turns out that the first 3 choices, empty set, singleton x, and singleton y, quite quickly lead to a contradiction. So that means the only possible choice here is that question mark is the set of x and y. And that leads to this top row, to this thing, that if I have 2 elements that are available after, well, if I have 2 delayed elements, then I have to take one step out. That was this one step that I got here. And then I need to apply my distributive law to whatever is left. And that's exactly what parallel computation does. And in the same way, we can show that the second row there also has to do exactly what parallel computation does. But now we're back at parallel computation. And we know that that doesn't work. But via this proof, any possible distributive law has to be parallel computation. So that means that there's no distributive law possible for power set. So that closes Rasmus's question. Does the delay monad distribute over power set? Nope. Nope, it doesn't. And this same proof also works for probability. So in the beginning I said probability and power set are very much alike. Now this slide where I've shown that it has to be parallel computation, if I just change my squiggly brackets for round brackets and my comma for a plus p, then I have the exact same proof for probability distributions. So it works the exact same way, except that I have only 3 choices, because probability distributions, they need to add up to, the probabilities need to add up to 1. So the empty probability distribution is not a probability distribution, so that's why there's like empty is missing here. I just have 3 cases, and then in the same way as power set, I can just go through those cases and prove that also for probability, it has to be parallel computation. But we had this general result about parallel computation, that as soon as I have a structure where I can put 2 things in, then it's not a distributive law. And this plus p operator, that's a structure where I can put 2 things in. So parallel computation does not work for probability distributions. Exact same proof. Now, if it doesn't work for power set, and there's nothing for probability distributions, can we generalize this even further? It turns out that we can. So in this paper, which has the same title as my talk, What Monads Can and Cannot Do with a Bit of Extra Time, Rasmus and me show that there's no distributive law for any monad over the delay monad, as long as that monad can be described by an algebraic theory that has an idempotent and commutative term. So you see, idempotence is really key here. It's that evil property that just breaks things. Also, if you go to my PhD thesis, like idempotence, it always breaks things. Slight footnote. I say causal here. Now remember at the beginning of the talk I said there were two versions of the delay monad. The co-inductive one, which we have been looking at so far, and the guarded recursive one. Now it turns out that any distributive law of a monad over the guarded recursive one automatically yields a distributive law for the co-inductive one. And these distributive laws are causal. But it turns out that it doesn't work the other way. So there are distributive laws for the co-inductive delay monad that do not come from a distributive law for the guarded recursive monad. Now these are weird distributive laws. And we have a toy example in the paper. It has to be a toy example because they're strange behaviors, because they don't respect quantification over clocks. So it's a strange example, but it's there, and that's the important point. So it is possible to have a theory, so a monad that has a theory presented by something with an idempotent and a commutative term, and have a distributive law for that monad over the delay monad. But it's weird. That's the takeaway. Like, you can only do this in weird ways. And not for power sets and distribution monads. Those are just definitely out. So only for very weird M does this work. But not all is lost. I want to give you a tiny bit of hope regarding distributive laws before I want to move on to free combinations. And like, so far, all my reasoning has been, well, if you go this way around the diagram, you have 2 steps, and if you go that way, it's only 1, and those are not the same. It's a bit pedantic. It's true, it's not a distributive law, but I mean, come on, with all the computers running at different speeds, who cares about if it takes exactly 2 steps or exactly 1 step? Like, can't we just say that that's, sort of similar? And it turns out you can. You can consider the delay monads, and it's called up to weak by similarity, where you consider anything as long as it terminates in finitely many steps to the same value, then it's the same element. So if I have x available after 3 steps or x available after 100 steps, that's the same. Now, complexity theory people might say, whoa, that's a bit too much. But these are only the 2 steps I can do. I can do either be pedantic about every step, or all finite steps are the same. Those are the 2 modes I can be in. But if you're in the weak setting where all finite steps are the same, then parallel computation is actually a distributive law. As long as your theory is not too weird. There are drop equations, which when you have a variable on the left-hand side, then it doesn't appear anymore on the right-hand side. Logical and or work in this way. Like, if you have x and x or y, that's the same as just x, so the y disappears. Those equations are no good. Like, we don't want to look at those equations. If you have a theory where there's equations, but then only the variables on the left-hand side also appear on the right-hand side and vice versa, so no dropping of variables, then parallel computation is a distributive law. So that's nice. And with that, I conclude my part about distributive laws, then as a little sort of dessert, I want to quickly mention free combinations, because distributive laws are a very particular way of combining monads. They're my favorite way because I do most of my research in them, but they're definitely not the only way and not the only useful way. And free combinations, they're much easier. So what you can do if you want the free combination of power set and delay monad, what you do is you take the axioms of the power set monad. So here are the non-determinism axioms that we've seen before. And then I take a now operation and a step operation. And then I just put them together into one theory. Then I get the free combination. And Rasmus and Andrea, they figured out that the monad that describes them is given by this guarded recursive equation, where so you have this P diamond, which is then the new combined monad. It's given by a set of either things available now or things available later. And these things are then again elements of this new sort of delayed power set combination thing. So if you keep unfolding this, then you get a set with some elements and some computation steps. And then once you do those computation steps, you get a set with elements and some computation steps. So you have this interleaving of sets and computations. And you can't disentangle them because you don't have a distributive law that allows you to get that interaction. So you're stuck with this interleaving. But it does turn out to yield a useful model. And it's a useful model for May convergence. So if you have a non-deterministic program, then you can see this as a tree with all the non-deterministic choices as branches. And if you have a distributive law, then you can look at convergence of all of these branches. You can go down each branch and see what values they end up in. But it could be that some of them get stuck in a loop and just continue running forever. And if you don't care about that, if you only care about a single branch terminating and the value in that branch, then you can use May convergence, which is what this monad describes. So Rasmus and Andrea worked this out in their paper, and they show how to reason with this monad about May convergent programs. And we recently tried to do the same with the distribution monad. So now we take probability distributions, and we do the same sort of free combination. So we have the axioms of a probability distribution, a convex algebra, and then we put a now and a step, we put them together, and we have this interleaving. So we have a distribution which gives some elements with some probabilities, but the probabilities don't add up to 1 because some elements have not finished computing. And then after one step, then we have a bit more elements. So the probabilities, they get a bit bigger, but they're still not equal to 1. And then you can compute a bit more, get a bit more probability. And that's this free combination of probability and delay monad. And in a paper that is now under review, Rasmus and me have gone together with Lars Bierkedal and his PhD student Philip Stassen and his postdoc Alejandro Alacoya. And we're looking at this monad and using it as a model for recursion and probability in type theory, in Clarke-Pugel type theory. And it works actually quite well. So using this monad, we can model recursive probabilistic programs such as a geometric series, which is flipping a coin. And if it lands on heads, then we stop flipping. But if it lands on tails, then we flip again. And modeling that recursive probabilistic process, we can do with this monad. So in this currently under review paper, we show how to model that and how to reason with that. So hopefully that will appear soon. So it's to appear to show that free combinations are indeed useful sometimes. And I invite you to do this with your favorite effects. Like of course there's work to be done, like otherwise it wouldn't be a paper. Like you need to actually show how to then model useful things with it. But you can try it with your favorite monad. Just if you want to have your favorite monad plus recursion in type theory, you can make this free combination. It's a monad, and then you can see what it models, see if anything useful comes out. So yeah, with that, I want to conclude. So I've shown you several options for distributive laws. Sequential computation did not work for power set, but it does work if you have a balanced theory. I've shown you parallel computation, also does not work for power set, but it works up to weak by similarity. I've shown you that there's no distributive law for power set and also not for distribution monad, both over delay monad. And that result can even be more generalized if you're willing to look up to causality. And yeah, I've referenced some papers. There's of course more in those papers if you're interested, because it's impossible to present an entire paper. So yeah, go look those up, and thank you for your attention.
Thank you.
Yes, thank you very much. It was very interesting. I wondered, I mean, you have answered this, but if you replace the delay monad, you know, the partiality monad, then maybe these problems disappear?
So the maybe monad, or?
No, partiality, is basically what you said, that you only difference terminating and non-terminating computation.
Yeah.
You get this from the free omega, the monad introduced by the free omega CPO over set. And we have written a paper in type theory about this.
I'll look it up. Yeah, thanks.
There's another, sorry, do the other people want to say something? But anyway, I just want to remark one thing. I gave a talk yesterday where I actually discussed issues with having the partiality monad, I mean, the finite set monad compared to the multi-set monad, which has to do with it's not a normal container, but it's a different kind of container. Mm-hmm. So there's maybe we can discuss this.
Yeah, let's discuss definitely.
Thank you for this presentation. I appreciated the fact that you showed exactly the points of failure and the examples, and we followed along the two paths in the pentagonal laws. So to that point, I saw that the points of failure, both of them were of the sort, on the codomain of these two paths, there was a L, right? And there was things wrapped in L, in the delay monad. Yeah. And I was thinking, okay, if you quotient by the weak by similarity, you're fine, you get a distributive law. Mm-hmm. What if you impose an order? I hope the question isn't too brain dead, and if it's not, you probably have thought of it. But what if you impose an order on the L, on the arrows with codomain L, and you ask the question, is it a lax distributive law? Have you thought of that?
Oh, I have not. I've not looked into lax distributive laws, but that's a very good question. I'll have to look into that. I'll probably ask to write it down because my brain is a sieve, but I want to look into this. Thank you.
So in the beginning, you opened with saying that all monads are presentable essentially by signatures and equations, right?
Well, so the ones I'm looking at, but yeah.
Yeah, indeed. So you were looking at specific kinds of monads. But that brings me actually to one of the questions I had now on your free combinations. Is this the same, I don't know if you're aware of this, but there are Leuven theories, which are can be used as a representation, and there's a construction of a tensor product of Leuven theories. And I was wondering if what you were showing is that, or if it's something else.
Yeah, I think it's the same, yeah.
All right, okay. That's good to know. So then there's actually a good amount of things you can probably reuse from there.
Yeah.
And then in that direction, there's a lot of work that has been done on disproving that there are distributive laws. You may be aware of that. In particular, there's a nice paper by, I think, Bartek Klin and someone else, who prove that there are certain distributive laws don't exist. That might be useful to
Yeah,
have.
no, it's one of my favorite papers, that power set does not distribute over itself.
Yes,
It's,
but one of the insights you gain from there is also that the problem with power set is indeed the idempotence does not count, if you wish. And so the way to fix this is introduce counting into the power set, so you have multi-sets.
Yeah.
And that, for example, gives you the distribution of the
Yeah, a lot of things can be fixed by looking at multi-set rather than power set.
Yes.
And, yeah. But then you don't have power set anymore. You have a different monad.
Yeah.
Yeah.
So maybe one more question. Yes.
Okay, so this is maybe a kind of a naive question, but your remark on the drop equations reminds me of the problem you have in PCF with, like, when you need to introduce parallel OR exactly for similar reasons, that, like, when you look at OR in domain theory, you need kind of you need to kind of choose a side, which is the one that's going to make the OR blow up if it diverges, and it seems to be very similar to what you have here. So I wondered if there's, like, any deeper connection or lessons you can learn, because I mean, domain theory people have looked at these kind of things quite hard. So
I'm not a domain theory person.
Okay.
I'm learning to be one. So this is definitely something I need to look into then.
okay, yeah.
So yeah, this came from Louis Parlant has done his PhD thesis similar in the same time as I did mine, and then we were looking just at this universal algebra and these equations, and it turned out that this balanced and non-drop, that those were like useful properties to look at. And I think it goes all the way back to Gautam. He has done some work also on this type of equations, but in a sort of completely separate from domain theory. So I really need to look into that.
Yeah, we can take that offline.
Yeah.
Thank you.
Any more questions? Maybe I can comment, like, the connection with domain theory is that the Kleiseli category of the delay monad is CPO enriched, right? So you can go into the framework of restriction categories and you can actually give a universal property for this monad. So maybe that's the, okay. So I think let's thank the speaker again, and we'll take a break.
Thank you.